Thank you everyone for being here. My name is Henrique, and today is my great pleasure to be here to talk to you about how we can use Julia to optimize trajectories for robots with legs. So first, I'd like to get started with a bit about my background, and so I can give you a bit of context on the work that I've been doing. And I'm originally from Portugal, where I did my undergrads and my bachelor's and my master's in computer science. And then I had the opportunity to go to the University of Edinburgh as an exchange student, and that's where I took my first course in robotics. And you can see here on figure number 1, the final project for this course, which was like a robot put together with Legos and other off-the-shelf bits and bobs of electronics, and it had to go around the maze picking up cubes with specific images. It was really nice, and it really got me hooked into robotics, so much so I ended up staying for other 4 to 5 years doing a PhD and postdoc there. So yeah, that happened. And that's where I stayed until 2022, and more recently I switched from academia to industry, and currently I'm a robotics engineer at a company called Ocado in London, where we do autonomous pick and placing of groceries. So it's a company, it's mostly known for being an online supermarket, and you order your groceries, and then the warehouse is almost fully autonomous, and there's these robots on wheels that move boxes of groceries around, and then there's these robot arms either with suction cups or grippers that pick and place the groceries from those boxes to the customer bags and then deliver them to the customer's home. So they were very kind in sponsoring part of my trip here by paying for my flights, so thank you very much for that. But today I'm here to talk to you about how I've used Julia for optimizing trajectories for robots with legs. So those are the robots that you can see here on figures number 2 and 3. In the beginning of my PhD, one of the first research projects that I started to work for was with this amazing piece of technology like the robot on figure number 2. And this is a humanoid robot called Valkyrie, and it's made at NASA Johnson Space Center. And it's 130 kilos, and it stands at 1.80 meters tall. And it's very complicated, and it's very nice when it works and very frustrating when it breaks. At the time, what I was doing is planning the whole body configuration. So what that means is I was trying to find the joint values for all the joints on the robot to be able to reach out for things, grasp bottles, and to also select carefully the foot placement on complicated terrain. But you know, at this point I was using C++ and Python, and Boston Dynamics kept publishing all these crazy videos of robots doing backflips and jumps, and I really wanted to start looking into more transitioning from planning whole body configurations, like a single whole body configuration, and switching to more planning agile motions and dynamic motions. So it turns out that if you want to optimize these kind of problems for robotics, the constraints are quite involved. And if you want to do research like I was trying to do about trying different cost functions and changing cost terms, I was doing very quick prototyping, and I was using finite differences at the time. So it was really, really slow and really painful. And I thought there must be a better way. And that's when I learned about automatic differentiation. And since I was using Python and C++, I was looking for alternatives. And I'm not sure if that has changed over the last few years, but when I was trying it, it was a huge pain as well. I remember that I tried a Python library for autodiff, and it had lots of constraints on how you were able to write the code. So for example, if you had a for loop, you had to unroll the for loop. If you couldn't have if statements. And then C++ was also very verbose. And I was finding myself in this situation where I was thinking about robotics problems, which were not necessarily very easy to think about. And then instead of having a language that was helping me get those problems across, I was having to fight Python and C++, which it's really not what I wanted to do. And so I was almost ready to give up and to try a whole different topic altogether. But I decided to give a few more quick Google searches, and I found Julia. And I mean, I'm pretty sure that you all went through this stage. You found I mentioned to Julia about like these auto differentiation capabilities, forward diff, the performance promises, like all the nice packages. It was really too good to be true, or was it? And then I decided to give it a try. I started using the Julia language and the packages in the Julia ecosystem for a few different toy problems. And it was amazing, and it really worked. And like this problem that I was having about having to fight the language, when I was using Julia, I found that it was so easy to get the ideas across and just to prototype quickly. So in summary, I think I switched for the autodiff and I stayed for the rest. I guess that sums it up quite well. So let's start with the robot demo and try to get a bit of your attention on the nice video. Is it? Okay. So this is the final demonstration video of one of the projects that I probably like the most during my time at Edinburgh, and it was like at the end of my stay there. And it's also this was for an European research project for offshore platforms and renewable energies. And so this is in the lab. It's a mock-up environment. You see the scaffolding. It's all normal scaffolding that we put together. And you can see a few different objects that the robot can interact with. You can see a wheel, you can see the lever. And you can notice that like on the bottom of the video, there's a few labels that keep switching. And so currently the robot is walking, and you see that the operation mode is in teleoperated. And what this means is just that in my hand, I have like a remote controller, like a gamepad controller, and I'm just pushing the joysticks in the direction I want the robot to walk to. And this is a functionality that it's available off the shelf when you purchase like the quadruped from this company. By the way, it's called Animal Quadruped from Robotics in Switzerland. However, you notice here when it, for example, when it reaches this door or this gate, it changes into autonomous mode. And this is because it's really hard to teleoperate robots to do these kind of complex motions. And you can see that the whole body moves in a coordinated fashion. So the arm and the quadruped. And I should also add that the arm is made by a different company and it's running a different controller, and these were not designed like to be put together. We just like put them together, and the trajectory optimization is considering the robot as a whole. But that you cannot buy off the shelf, you know, you have to do it. And so that's what I want to say, is that the autonomous mode that you see here is Julia. Everything being planned, the motion planning is in Julia. Here, this task is particularly interesting because there's a bucket with a rope, and the robot needs to pull the rope to lift the bucket to a specific height. But just using the arm is not enough. So you're going to see it's taking steps at the same time as it pulls the rope by moving the arm. And these are very complicated problems in robotics. It may not seem like much, but it's a lot of work to get this to work on the real robot. Because you have like all these contact interaction, the breaking and making of contacts, and the external disturbances and the forces going on. So it's really, really interesting to look at this problem from a research perspective. So let's see how we can plan these kind of motions, the ones that I showed in autonomous mode. Let's see how we can do this using Julia. And but first, I want to give a quick introduction on what trajectory optimization is. And I'm not sure. I mean, I know there's a few people from robotics in the crowd, but I'm not sure if everyone knows the basics. So I'll just quickly go through it. There are two robots here on the right. There's a robot arm, and then there's a quadruped robot. They have a few similarities, but a few differences as well. The robot arm here has 6 moving joints, each of which with an actuator. And so to represent the state of this robot, which is the X over there, you can represent it using a 12-dimensional vector, the 6 positions and the 6 velocities at the current time, okay? And this is called a fully actuated system because there's a motor on every joint, and so we can directly change the state of the robot by moving the joints, by commanding currents or torques to the joints. However, in contrast, the quadruped, it's an underactuated robot. And there's a nice course taught here at MIT by Professor Henrique on underactuated robotics. And the main difference is that the quadruped is not fixed. It's not screwed on a table, or it's not bolted onto the wall. It can move around. And it does have motors on the legs, but it does not have a motor on its torso. So if the quadruped robot is standing on this corner of the room and I want to move the robot to that corner of the room, there's no magical motor that I can just actuate to just magically move it there, or there's no jetpack to make the robot fly there. So what you end up having to do is you need to find the correct motion, so that the torques that you need to send to the motors on the legs to somehow move the robot there, either by jumping, by walking, by running, whatever. And so that's the main difference. And then there's also the contact force interaction at the feet, which needs to be handled properly. So in summary, for trajectory optimization, we need to be able to quantify state, controls, the dynamics of the system. The state, as I said, are the joint positions and the joint velocities concatenated. And for the quadruped, this includes the additional coordinates for the position and for the orientation of the torso, which is like the origin of the robot. And then what are the controls? Well, the controls that can change the state of the robot are the torques that we can apply at each of the motors and the contact forces that are exerted on the system. So these would be, for example, when the robot is, the feet are on the ground, these would be the contact forces that the robot experiences from the contact interaction. So how are these related? These are related by the very famous equations of motion, which is that equation there on the bottom left. And I'm going to gloss a bit over the details, but essentially what they show is the relationship between the state and the control. So how do the controls affect the state? And they can give us the answer to questions like, if my robot is at a specific state right now, and I want the joints to accelerate in a certain way to reach another state, it can give us the torques that I need to apply at the motors to achieve that acceleration. Or we can look at the problem in the opposite way. So say if we are simulating, if we're writing a simulator and we have the robot in a specific state, and I know the torques that I'm going to apply, we can use this equation to compute the joint accelerations that are a consequence of applying those torques. And so that, I think, summarizes pretty much the state, controls, and dynamics. And any questions up until this point? Yes? So okay, this I'm going to talk about next. Yeah. Yes. So this gives us the basic building blocks, okay, to describe the state and the controls to the system. But now we are going to get into the trajectory optimization problem, which is the interesting bit where we can start adding constraints on what the robot should do. So what's the trajectory optimization problem? Essentially, we have an initial state, the state where the robot is currently. We have a final state. This is where we want to go. And then we have the system dynamics. And our goal is to find a sequence of the controls that we need to command to the motors to move the robot in a specific way from the initial state to the final state, okay? So that's pretty much what we have to do. And this is where we can add some constraints, but I'll go into a bit more detail on that as well. There are multiple methods which we can use for solving these kind of trajectory optimization problems. But today, for the purpose of this talk, I'm going to be describing direct transcription, which is my personal favorite. And the reason for that is that it's very simple, and I'm pretty sure that every one of you will understand this and will be able to go home, and if you want, you can implement this yourself. The philosophy of direct transcription is to discretize everything. So let's consider this plot here where you have time on the horizontal axis, and x is the state of the robot. So this is a multidimensional axis. Discretize everything, so we start by splitting the trajectory, the duration of the trajectory into different time segments. And at the beginning of each segment, we are going to represent the joint positions and the joint velocities of the robot at the beginning of that time segment. Okay, so those are the blue dots in the plot over there. In addition to this, we are also going to represent the torques and the forces that we are going to command to the robot at the beginning of each time step, okay? And so now you notice that there's some blue lines coming out of these blue dots. And the reason for that is that we can now get, with this information, like at each time slice, we get an idea of how the system evolves over time. So again, from those torques, for each joint position and velocity at the beginning of the time slice, we can apply them. And according to the equations of motions, we can get the joint accelerations back. And then using your favorite integration method, you can integrate those accelerations to check how the state evolves over time. Does that make sense? Okay. You can also notice that, however, the plot doesn't look right. Like there's these massive gaps and discontinuities. And the reason for that is that we're not really sure what the trajectory looks like in the first place. That's why we're solving the trajectory optimization problem. I mean, the initial values for what the trajectory may be, we can say that they're all zeros or they're all random. Or we may have an educated guess, but it will look something like that. It will not make sense. And so what we want to do is we want to be able to quantify these things called the defects. We want to be able to calculate the values of how far off we are. And if we are able to quantify those, we can pass them, we can formulate a nonlinear equality constraint to the solver saying that they must equal to 0, right? And then after a few iterations, the solver will do its magic and it should eliminate those defects by tuning the correct values for the positions and the velocities over time. And it will lead to like a fully connected trajectory. And oftentimes we just like discretize it more finely so we get a better representation of the trajectory. And so you end up with this beautifully smooth and connected trajectory. It doesn't have to always be smooth, by the way. But that's it. Pretty simple, right? So this is a summary of the whole thing. We divide time into segments. And then the decision variables in our optimization problem, they are the joint positions, velocities, torques, and contact forces for all the points that we have discretized. And then the constraints are the system dynamics. And by the way, I'm using a package in Julia that considers the full order system dynamics. So this will reason about the masses and inertias of every single link on the robot, which is really nice. A bit more computationally expensive, but it will be worth it. I'll show you why. And so the constraints are the system dynamics, just to make sure that the robot moves like a robot. The contact forces is like, so if my foot is off the ground, it cannot experience any contact forces. That makes sense. But if it's touching the ground, then there needs to be a contact force from that interaction. And then there's also a constraint on where that force is pointing. There's a concept called a friction cone. And essentially, if the force is pointing outside the boundaries of this friction cone, it basically means that the object is sliding. And so we don't want the feet to slip. So we need to enforce constraints for that. And then there's other task requirements, like if I want to grab this bottle, my end effector must be here. And if I want to take a few steps, then I have constraints on where my feet should be. Once we have transcribed all of these constraints into something that can be digested by nonlinear solvers, we can formulate high-level problems and then have trajectories that look something like this. So this is the quadruped, and it's going to jump forward. It's a 3D visualization of the trajectory. You can see in yellow the contact forces, and in green the paths for the end effector. The paths were not encoded whatsoever. These like emerged out of the constraints that I formulated. And so maybe just again, you can see other things like the projection at the center of mass. But essentially what has happened here is that I said the feet must be here at the beginning, the feet must be there at the end of the trajectory. In between, there's an interval in time in which the feet are not constrained to a specific place, but there cannot be any contact forces. And so the solver figures out that the only way to do this is by jumping. And then there's like also this nice video of the humanoid. It's 90 kilos and all electric motors. So it's a very small jump, not at all like Boston Dynamics, but I'm still nonetheless very proud of this jump. And you can see the beautiful behavior, like what I was referring to about like using the full system dynamics. The initial guess for this problem was the humanoid just standing still, like repeated, like the joint positions were the robot standing still for every point in time. And nonetheless, you can see that the solver finds like this nice arm motion, like to generate momentum to jump. And these were not at all encoded in the constraints. This is an emerging behavior. Okay, I'm running out of time, so I'll try to be very quick. Julia packages for robotics. These are these are amazing packages, and I have a lot to thank to the Julia community for having these ready and available for us to use. IPOpt and Nitro are the wrappers to off-the-shelf nonlinear programming solvers. Rigid biodynamics are for the algorithms that take care of kinematics and dynamics of complex mechanisms. Sparsity detection, forward diff, and sparsity if tools. Like, these constraints are very sparse. It's basically, if you think about the dynamics constraints, the Jacobian is like block diagonal, very sparse, and each block is also sparse on its own. So it's very important to use this so we get every bit of performance we can. Static arrays for non-allocating arrays. Meshcat for the visualization, robot operating system for interfacing with the rest of ROS, and then revise so we can update functions. Revise is amazing. I'm pretty sure you know that. Demo, and fingers crossed because live demos never work, right? So I'm going to show you a demo of Tora.jl, which is a library that I wrote for optimizing trajectories for robots with, for robot arms. The reason why I wrote it is I wanted to give something back to the community, but I was too ashamed of the spaghetti code that I wrote for like my research prototype code. And so I decided to start small by just doing the library for robot arms. And essentially it takes oh, why is it not showing? I'm not sure why. Okay, I have to stop the presentation. So these are the documentation. It takes the robot model. URDF is like a very well-known format in robotics. It takes a high-level problem description, and then essentially it takes care of everything that I've just told you about. It takes care about converting these high-level problem descriptions into the mathematical constraints and cost functions that the solvers can take, and then it digests that and outputs a robot trajectory. So let's quickly go through the demo before the questions. I already run it beforehand, so it should work. And yeah, you can see here that essentially what we're doing here on the Jupyter notebook, I'm loading this cell is loading the 3D visualizer, and then on this line I'm loading the robot arm. Is called the white robot arm you see there is called Panda from a company called Franca, and then we are creating a high-level problem description using Tora for this robot. And we're going to discretize the trajectory into 201 points. That's the number you see there. Maybe I can make it a bit zoom in. And then we're going to use a frequency of 100 hertz. And so essentially, if you use 100 hertz and 201 points, you obtain a trajectory of 2 seconds. And now we are going to start adding constraints. And for example, if I want the robot to start from a standstill and then the trajectory at a standstill, this is the kind of high-level constraint that I was talking to you about. We can just say, fix the joint velocities for this problem, for this robot, at the first point of the trajectory, at the last point of the trajectory, and I want them to be all zeros, okay? And then this for loop is basically saying, I want the hand of the robot to trace out a circle in space. And then the next thing we do, and the dynamics are already by default enabled, so you don't have to worry about that. Then this bit is defining the initial values to the problem, and you can see that, can we see that? Maybe I need to refresh this. Oh, you already saw the spoiler of the motion. Damn it. But you can see there, these joint positions, the ones currently being shown, are the ones that are repeated for every point of the trajectory. That's our initial guess, even though we want to trace a circle. It doesn't make sense. It doesn't have to. The solver will handle it for us. The velocities and the torques, our initial guess is just going to be all zeros. We don't care. It will just work. Then on the next cell, I have a bunch of options for the solver to make it work like faster, but if you use the default ones, it works reasonably well as well. We just call solve. So if I call solve, you can see that it takes 10 iterations. This is, again, a single thread and using the full order system dynamics. And it takes around, like, if I run it a bunch of times, you can see 150 milliseconds. Sometimes it takes less, depends on the weather, I guess. Now we can play the trajectory, and you can see that it's very nice, it's very smooth, and you can see that if we were just planning a motion with respect to the kinematics, so just the positions and the velocities, with the initial guess that we use, it would probably look very robotic. Like it would just like snap the configuration into each target. But you can see, however, the there's a very smooth way, like in the way the wrist moves. And this is because we are using the full system dynamics in the constraints. And I think it looks really cool. And then we can also plot, again, the positions over time for each joint, the velocities, the torques, and then this is like the feasibility error over the iterations. So that's pretty much it. So live demos can work. Thank you. Just to finish off, like I know that there has been other people talking at JuliaCon in other Julia conferences, so I just wanted to put them here. The work that Robin and Tuan have done is really amazing, so do check that out on YouTube. And they focus more on the controls. Today I focused more on the planning, and I know there's also a lot of activity in Julia Robotics about the perception, so do check that out if you're interested in robotics. And with that, I would like to thank you all for your attention, and I will be taking any questions.
What do you think? Sorry, the next step.
Oh, okay. Is this one working as well? Okay, there you go.
What would you say are the next steps for this project and going forward for you are for the next year or so?
This was my work when I was working in academia.
Yeah. So you're not continuing that?
I mean, I sometimes still work on it, but I have like very little time in my free time to work on it. But yeah, so I don't have like any big plans. But on my free time, I sometimes like improve the performance or add additional features to the library. Yeah.
I saw that you mentioned you are using sparse diff tools and you're creating the NLP model that you pass to ipop.jl, right?
Yes.
So basically, like, how do you? Okay, I see. I wasn't aware of sparsity detection.jl, so I was actually going to ask, how do you get out the sparsity structures, basically?
Yes. So if you the code is online, so you can check that on GitHub. But essentially, for every function that I use in the optimization problem, either for constraints or for the objective, I first pass it like some dummy inputs to get some dummy outputs, and then I use I calculate the sparsity of that, and then I use forward diff to in place get the values of the sparse automatic differentiation of those functions.
And just for an estimate, like how many parameters do you have in these optimization problems?
Okay, I think, I don't know by heart because it keeps changing. But for example, this one, again, it was, the summary it's here is like 2 seconds, 201 knots, and a few constraints, like the dynamics constraints and everything. You can see that this problem is like number of non-zeros in equality constraints, like 34,000. The number of variables are 4,200. But, you know, it works as well. If we increase this by an order of magnitude, I do hope it works. So now we are saying, it's going to be, again, 2 seconds, but we are going to use 2,001 knots, and we are going to use 1,000 hertz. So this is like a very fine discretization. And if I run that again, it will take a bit longer. So instead of 10, it took 14 iterations and 1 second for 100 milliseconds. And you can see that now everything also increased by roughly an order of magnitude. So now this optimization problem has 42,000 decision variables, 28,000 equality constraints, 3,000 inequality constraints. Like they are pretty big problems, and especially this is for a simple robot arm. But when the optimization problems for robots with legs, where you have the contact forces, they can get pretty big.
Okay.
Thank you for a nice question.
Hi. Amazing talk. Thank you very much. So I had a question as well, just in general with the Julia robotics ecosystem.
Maybe can you speak a bit? Yeah.
Yeah, sorry. Things like, so you use, for example, ROS to, use Julia with these robots. Things like ROS2 are not yet supported in Julia very well, or, moving forward, you've used rigid body dynamics, but things like, other robotic simulators like Majoko aren't supported in Julia very well. Can you give any comment, I guess, in the field? Do you know of anyone working on those kind of things, or if there's any development within the Julia robotics ecosystem?
Yeah, so unfortunately, Robin and Tuan they don't have so much time to work on the Julia packages that I've mentioned because they're now working at Boston Dynamics. And there's a lot of work on the perception thing. I think I'm not so familiar with those packages, but I think it's Caesar.jl. So for localization, I think they're doing SLAM. For the demo that I showed in the beginning of the talk, that was using ROS1, so Robot OS.jl took care of the interface. For ROS2, I'm not working on it. I don't know if anyone is working on the wrapper for that. And about Mujoko, what was the question again? Sorry.
Just other simulators like Mujoko.
I think there's an old interface for Mujoko, but it's a bit old. Yeah. And okay. Okay, I'm really sorry. I'm already over time. So thank you very much, and let's give some room for the next speaker.